So what we're going to be covering today is the Lewis structure diagramming procedures. As you can see here in the left-hand side, there are a series of steps or rules that you can follow. If you follow these rules and apply them each time you create a Lewis structure, you'll subsequently get a healthy structure. What you need to understand is, in addition to these rules, you should always have a periodic table. The periodic table that you see over here is going to allow you to establish things such as position in the table, number of valence electrons, and things of that sort. So the use of these two tools will allow you to effectively create Lewis structures. So let's go ahead and let's actually do a practice problem in order to prepare ourselves for actually writing these Lewis structures. So let's go ahead and let's look at an example. CF4 is the molecule, or carbon tetrafluoride. And basically what we're going to do is we're going to figure out step number 1, which is to find the total number of valence electrons from all of the elements. Okay, so carbon and fluorine are the two elements that make up this molecule. Now, in order to figure out the valence electrons, we have to look at our periodic table for each of the individual atoms. Okay, so if we go ahead and we look at our periodic table and we go find carbon, you will see that carbon is number 6 on the periodic table. Okay, so in order for you to figure out how many valence electrons carbon has, you need to look at the previous noble gas. And in this situation, helium is the previous noble gas on the periodic table. So what you do is you count from the previous noble gas until you reach the element that you desire. So if we count from helium, we have lithium, beryllium, boron, and carbon. That's a total of 4 spaces. And those 4 spaces represent the 4 valence electrons that carbon has. Okay, if we do the exact same thing with fluorine, who just so happens to have the same previous noble gas in helium, if we count over lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, you subsequently are able to calculate that each fluorine atom has 7 valence electrons. Now, we're not just asking for the valence electrons of the individual elements, we're also trying to figure out the total number of valence electrons in the molecule. Okay, so we have to account for the actual number of atoms that are in this molecule. So, according to our molecular formula here, we see that carbon has no subscript, which implies that there's a 1, right? So we have 1 carbon. So we're going to multiply our number of valence electrons by the total number of carbons, which is 1. If we look at the fluorine atom, we know that the subscript is 4, and we're going to subsequently multiply by 4 in order to figure out the total number of valence electrons coming from those fluorine atoms. So 4 times 1 gives me 4 electrons. 7 times 4 gives me 28 electrons. Now, this is the total number of electrons that are coming from each individual atom type. Now, in order to do a Lewis structure, we need to account for this total number of valence electrons. So we do a summation. So basically, we add up our total number of valence electrons from carbon and our total number of valence electrons from fluorine, and we subsequently get the total number of valence electrons for the molecule. This now allows us to move on to step number 2. Which tells us to put the least electronegative element in the middle. Okay, so I have to choose between carbon and fluorine. Now, you guys know that fluorine is the most electronegative element. It's the one that desires electron density most intensely. Okay, so carbon, by default, has to be the least electronegative element. So what we're going to do is we are going to put carbon in the middle of our structure, and we are going to surround it with the remaining atoms. So in this case, with our fluorine atoms. Okay? Now, so we've finished step number 1 and step number 2. And what we're going to do now is we're going to move on to step number 3, which tells us to bond each element to, each exterior element to the central element. Now, in this case, fluorine is going to bond to carbon 4 times. Each one of these bonds that I have just drawn represent 2 electrons. Okay, so 1, 2, 3, 4 bonds, so 4 times 2 is going to give me 8 electrons. So notice that on this right-hand side, I'm keeping a tally of the number of electrons that I'm using. So if we look at this, we can see that we have a total of 24 electrons remaining to be distributed. Now, in order to figure out where to distribute them, we need to go ahead and look at step number 4. Step number 4 tells us to distribute the remaining electrons so that each of the surrounding atoms has its octet. Okay, so fluorine, which is number 9 on the periodic table, wants to have a total of 8 valence electrons. So in order for it to have 8 valence electrons, we need to make sure that they have that exact number. So if we look at the example, carbon is bonded to fluorine. So each one of the fluorines that are bonded to the carbon already have 2 electrons in order to satisfy their octet. However, that would mean that there are an additional 6 electrons that each fluorine will need in order to be satisfied. So what we do is we distribute the 24 electrons to the remaining fluorines. So each fluorine is going to need an additional 6 electrons. So we're going to go ahead and go around to each atom. Notice I'm using dots to represent the electrons that I'm distributing. Okay, so I've distributed 6 electrons to each of the 4 fluorines that are surrounding the central atom. 6 times 4 gives me a total of 24 electrons. Okay, 24 minus 24 is going to give me 0 electrons left over. Okay, so I've completed steps number 3 and 4, and I now subsequently need to move on to step number 5 to make sure that everybody has their octet. I no longer have any more electrons to distribute, so we have to see if everyone's happy or if we need to take additional steps. So if we look at each carbon, if we look at the carbon atom, notice that the carbon atom is bonded to 4 fluorines. Each one of those bonds has 2 electrons. So 2 times 4 is going to give you a total of 8 electrons that are surrounding that carbon atom. So carbon has its octet. And then if we look at each of the fluorines, all of the fluorines are bonded exactly the same with respect to having a single bond and 6 electrons that are unbonded around it. So we can really just look at each of them or one of them as an example that will suffice for all of them. So if we look at the fluorine atom, notice that it has 2, 4, 6 unbonded electron pairs, and it has 1 bonded set. Okay, so 2, 4, 6, 8, a total of 8 electrons. So subsequently, you can see that this fluorine molecule is actually quite content. So basically, everybody has met their octet necessities. Okay, so that now leaves us to actually move on to step number 7. Okay, because everyone has their octet, we can skip over step number 6. So let's move on to step number 7. So step number 7 is basically the checking of formal charges. What you need to understand is that the formal charge on each element actually needs to or wants to be as low as possible. Basically, it's a bookkeeping methodology. The closer you are to 0, usually the better your structure is going to be. Okay, so the more zeros or the closer to 0 your formal charges are, the better off you are. Also, the sum of all the formal charges must add up to the overall molecule's formal charge. So, if we go ahead and we look at the example here, okay, so we have carbon as our central atom. So let's go ahead and let's start with that. Calculating carbon's formal charge, what we're going to do is we're going to utilize the formula you see in number 6. Okay, so the formal charge of carbon, okay, is going to be equal to the number of valence electrons, which we established earlier as 4 electrons. Okay, so what we're going to do is from those 4 electrons, we're going to subtract out the number of unshared valence electrons plus half of the bonding electrons. Now, carbon only has bonded electrons. There are no lone pairs on that carbon atom. Okay, so in this case, we're going to just have a 0 for our unshared valence electrons. Now, our bonded electrons, notice that carbon has 4 bonds around it. Okay, so each bond has a total of 2 electrons. 2 times 4 is going to give us 8. So half of my 8 bonded electrons around carbon is going to give me 4. So 4 minus 4 is going to give me 0. So carbon gives me a formal charge of 0. Notice I put the 0 next to the carbon and I put a little set of parentheses around it. This is how you'll typically see it in most textbooks. Now, the formal charge on fluorine is going to be calculated in a similar way. Okay, so once again, the number of valence electrons, okay, fluorine has 7. Okay, now my number of unshared valence electrons. Now, I'm going to look at each fluorine individually. You don't count up all of the electrons around all of the fluorines. You're only going to focus on a single fluorine at a time. Okay, so So what we're going to say is we're going to say, okay, fluorine has how many unshared valence electrons? Okay, so on the fluorine that we have circled, we have 2, 4, 6 unshared valence electrons. So we're going to put a 6 here. Now, fluorine also has bonded electrons. It has a single bond connected to that carbon. Okay, that single bond has 2 electrons. So half of those 2 electrons is what we're going to plug in for our bonded electron set. Now, 7 minus 6 plus half of 2 is also going to give us 0. Okay, so the formal charge here, okay, on fluorine is going to be 0. Now, we could go ahead and we could calculate the formal charges for each of the other 3 fluorines. However, because they are bonded identically to the one that we did our first calculation from, all of them are going to have the same formal charge. Okay, guys, make sure that you're putting those parentheses around those formal charges, and so there's no confusion between that and electrons. Now, the last thing we should check out is to make sure that our formal charges add up to the overall charge of the molecule. So remember, our molecule that we're looking at right here is carbon tetrafluoride, CF4. If you notice, there is no charge on this molecule structure. Okay, because of that, our overall summation should equal 0. And as we can tell, 0 plus 0 plus 0 plus 0 plus 0 is going to give us 0. So the Lewis structure that we've drawn here is actually really good. It satisfies the octet of each of the atoms. It has the lowest possible, or the closest to 0 possible formal charges, and you subsequently have what you desire. So this is the basic approach to figuring out Lewis structures.